Changed my mind. I'm actually going to do it live in person, just asynchronously, I guess, because it's not really live. All right, so first thing we need here is we need an f of x value. Right, so f of x is going to be whatever the function is. We need a value of a, we need the actual value of x, and then we need our linearization formula. Right, so I'm going to write it up here. Right, so f of x is going to be approximately equal to the linearization of x, which is f of a plus f prime of a times x minus a. All right, so we're also going to need a derivative. So maybe throw this down there a little bit. All right, so I'm going to need this for each one of our functions. So I'm just going to cheat for a second and just duplicate it. You can pause this video so you can do whatever you want. I could talk as fast as I want in these things. You could put me on 1/2 speed and I could really go back to being like an Italian New Yorker and talk super fast. So our first function is going to be cosine of x. Um, from the previous page, the derivative of cosine of x is negative sine of x. Feel free to go back and check that. I need a value close to 0.07 that I could take the cosine of. So once again, 0 would be a good choice. We can easily do the cosine of 0. And then the value of x is going to be 0.07. All right, so when I throw everything to our linearization formula, so we're saying that the cosine of 0.07 is approximately equal to this linearization of 0.07. And the linearization of 0.07 is going to be the cosine of 0, the easy value of a, plus the derivative. So it's just going to do a minus sine of 0 times our value of x, 0.07 minus 0. But this is going to be pretty easy because cosine of 0 is 1. Sine of 0 is 0, so it doesn't even matter what I get there. I'm going to get 0. So our linearization is 1. So what this is saying is that the cosine of 0.07 is approximately equal to 1. And again, we can check all of these things that we get, which I know kind of defeats the purpose, right? So we could easily just evaluate these things in the function to begin with, but the point is getting those values and seeing that this is really, really close to the value of 1, right? So like 0.20025 off. So if we did the same thing for cube root of 9, so what do I need? I need a function. So I'm going to go with the cube root of x, right? Again, if you're, unsure what the cube root of x is, you could write this as x to the 1/3, take your derivative, right? Bring our exponent down, subtract 1 from 1/3. This is really hard to evaluate anything in, so I would recommend writing this as 1/3 times the cube root of x squared. We need a value of a. I need something really close to 9 that I could take the cube root of. Well, I can take the cube root of 8 pretty easily. Our value of x was 9. So what we're saying here, give us a little space there, is that the cube root of 9, right? So f of 9 is approximately equal to the linearization of 9. The linearization of 9 is going to be equal to f of 8, so the cube root of 8 plus, well, derivative with 8 in it. So we're going to get 1/3 cube root of 8 squared times x minus a, or 9 minus 8. So that's going to be 1, so we don't really care about it. Cube root of 8 is equal to 2. This is going to be plus 1/3. So cube root of 8 squared is either cube root of 64 or cube root of 8, which is 2 squared. Either way, that's going to be 4. So this is going to be 2 and 12. So this means that the cube root of 9 is approximately equal to 2 and 1/12. 1/12 is like 0.083. So 2.083 repeating, something like that. Again, we can check our work. Right, so I could take the, whoops, that's cubing. Whoops, that's not clearing. So I could take the cube root of 9, 2.080. So again, right, we can see that our linearization is really close to this value. Natural log of 1.3. So we're going to need a function, right? We're going to take the operation natural log of x. The derivative of natural log is 1/x. I need a value close to 1.3 that I could take the natural log of. So the only things we can really take natural logs of that are easier are 1 and e that are anywhere near 1.3. But 1 is closer to 1.3 than e is to 1.3, so 1 is the better choice. And the value of x is 1.3. So the natural log of 1.3 is approximately equal to the linearization of 1.3. And the linearization is equal to the natural log of 1 plus 1 over x, so 1 over 1, times 1.3 minus 1. Natural log of 1 is 0, plus 1 times 0.3. So the natural log of 1.3 is approximately equal to 0.3. And once again, we could check it, right? So if we were unsure, natural log 1.3, boom, that's kind of close to 0.3. We'll see that the reason is the curvature at, so if we look at like this function, right, natural log, it looks like this. So 1.3, using 1, we're getting kind of that tangent line. So you get a much better approximation if we can get something where this natural log is a bit more kind of narrow, but again, you can't really do that. You kind of bound by the values that you have. And then 2.1 to the sixth power, well, f of x is going to be x to the sixth. The derivative of that is going to be 6x to the fifth. What's the value close to 2.1 that I could raise to the sixth? Well, 2's looking pretty good, and x is 2.1. So we're saying that 2.1 to the sixth power, right, f of 2.1 is approximately equal to the linearization of 2.1, which is equal to f of a. So that's going to be 2 to the sixth power plus 6 times a to the fifth power times 2.1 minus 2. Right, so f of 2 plus f prime of 2, x minus a. 2 to the 6, what's that? 64. That's 64. This is 32. 32 times 6 is 192 times 0.1. So that's going to be 19.2. 64 plus 19.2 is 83.2. So 2.1 to the sixth power should be approximately equal to 83.2. Let's see if we nailed it. 2.1 to the sixth, 85.76. Again, not too bad for a little bit of quick math to get ourselves to a value. 2 off with our approximation.